Hey guys, I welcome you all to this informative session by Great Learning. So, classification techniques are an essential part of machine learning. And today we'll go through one of the most widely used classification technique, logistic regression. With the help of logistic regression, you can identify whether a tumor is malignant or not. It also helps in tagging a mail as genuine or spam. And you can also use it to find if a credit card transaction is fraudulent or not. So there are a surfeit of applications of logistic regression. So keeping the importance of logistic regression in mind, we have come up with this comprehensive tutorial. The session will be taken by Professor Mukesh Rao, who has over 20 years of industry experience in market research, project management, and data science. Now, before we start off with the session, I'd like to inform you that we'll be coming up with a series of high-quality tutorials on artificial intelligence, machine learning, and computer vision. So please do subscribe to Great Learning's YouTube channel and click on the bell icon so that you get a notification of our upcoming videos. So in this tutorial, we'll start off by understanding the core concepts of logistic regression and then implement a demo with the scikit-learn library. So let's start off with the session.
The name logistic regression is slightly a misnomer. It is used for classification. It cannot be used for regression, okay? Though the name says regression. But there's a reason why it's called regression, not logistic classifier. The reason is, under the hood, logistic regression uses linear models, linear regression. That's the reason. It's a classification method based on a linear regression. The response variable, that is the target variable, can be binary class, defaulter, non-defaulter, diabetic, non-diabetic, or it can be multi-class classification also. I can use logistic regression for optical character recognition. I can do that. And in my personal experience, I have seen and I have also read some papers about it. When I compare models, often logistic regression comes out on the top. If not exactly on the top, at least top few, top 2 or 3, okay, for classifications. So I'm going to start by showing you binary classification, but this can be used for multi-class classification also. Given your independent variables, what is the class likely to be? That is the objective of this model. I can also use a function available in scikit-learn where instead of defining which class an observation belongs to, a test record belongs to, I can print out what is the probability that this record belongs to this class versus this class. I can even print probabilities. Okay. This particular function is nothing unique to this. It's available in all probability-based models. Predict, you remember we use predict? We just add underscore proba. This function will print out probability values. If you go for just predict, this will print out the classes. Decision tree also has this, naive-Bayes algorithm also has this, logistic also has this. Predict underscore proba. Let's take a hypothetical situation. Don't worry about the PPT. Let's take a situation and discuss this concept. And for that, we are going to use 3 colors. You are a data scientist, you're working in a bank, and you have been tasked with, you have been given a responsibility to build a model where the model will take certain inputs and the output of the model will be, is this person likely to default? If I give him loan, is this person likely to be a defaulter or a non-defaulter? You have to build that model, okay? So what kind of data will you need to build such models?
His salary income, his student or his profession.
So past history in terms of
CIBIL score.
CIBIL score, okay, CIBIL score is an output of a model actually. So let's keep CIBIL score aside. you'll need his age, gender, income, any past loans he has taken, any property he has, so on and so forth, so many things. Now let's assume that one of the things given to you is his income. Forget it, this is a touchy subject, so let's call it age. Okay, one of the inputs given to you is the age of the people. So you have the past data with you. The bank has given you a past data set. In the data set, you have both defaulters, non-defaulters, and one of the columns in the data set is age. You notice a pattern here. The pattern is most of the defaulters, okay, most, not all, most of the defaulters are in the lower age bracket, okay, and you also notice most of the non-defaulters are concentrated in higher age bracket. But that doesn't mean there are no non-defaulters in low age. Okay, you observe this pattern. Now, since there are two classes here, what we're going to do is we are going to say green class, we're going to assign a numerical value 1, red class numerical value 0. Remember, we can't work on string data types. So the target columns will be assigned numerical types. Okay. Why 1 to this, why 0 to that? No reason, you can flip it also if you wish. But we assign a value 0 and 1. We don't assign any other value, we assign only 0 and 1. There is a reason for that. Okay. Now, your object, yeah. Now you find that the pattern over here, as income increases, you find more greens. As income decreases, you find more reds. You have done a linear model already. So what you do is, you try to build a linear model here. So you say, let the y-axis be probability of belonging to any one of the classes, let's call it 1. The y-axis is probability of belonging to class 1. You can actually take it as probability of belonging to class 0 also if you like. The two probabilities will be inverse of each other. So you can take any one you like. Alright? So when you build a linear model, the linear model, anybody has a black pen here? Black? No, this pen. Oh, okay. Now you'll notice that as the age increases, if this is a probability, the probability of somebody being belonging to green, the probability increases linearly. Probability increases. I can represent it with linear models. If I had taken this as 0, if this was 0, then this line, how would it look? It will be reverse. That's the difference. So you can use any line. Okay. So I'm taking this as 1 for ease of explanation because you will be able to connect to what we did yesterday. So the line will look something like this. So this line, y equal to y is probability of belonging to blue class, is related to mx, x is this variable, plus c, c is the intercept over here. C may be 0, c may be negative. But the problem with the linear model is, linear models go to infinity, minus, plus. Probabilities have to be within 0 and 1. They can't be below 0 or above 1. So, we can't use a linear model. We use another technique where we transform this line into an S-curve. This S-curve is called a sigmoid. And it is very easy to achieve this. The sigmoid is nothing but 1 by 1 plus E. E is an Euler constant we use in mathematics, minus mx plus c. So this best fit line, the best fit line which is found for you, this best fit line is fed into this transformation, this mathematical formula. The result of this transformation is this curve. Yeah, sigmoid curve, the property is it will reach 0 at infinity, it will reach 1 at infinity. That's exactly the property of a probability distribution. Now let us interpret what this formula is saying. Keep in mind we're building the model, so which means we're in training set. So in training set we already know the labels of every record, right? The algorithm gets both the input variables and the output variable, x and y. So all the labels are already known. And the labels are shown in the color over here. Are you all okay? Shall we proceed? Now, what the models, now that I got sigmoid, I'll remove this line. I'll remove this line. Okay, this is going to infinity. We don't even need this. We don't even need this. Now, what this model is telling you, let's look at that. If you take this red point, look at this. If you take this red point, what the model is saying is the probability of belonging to blue class. What is the probability of this guy? Suppose we don't know the color. What is the probability of this point belonging to blue class? It's very low, which means it belongs to the red class. So the model prediction and actuals are matching here. The model prediction and the actual label, both of them are matching. Take this green one. What the model is saying is, what is the probability that this green point belongs to blue class? This is probability of blue class, right? The probability is very high. And he is actually green. So both prediction and actuals match. Right? Hey, lady, are you with me? Sure, 100%. Okay, don't get left behind. Your expressions tell me a lot of stories. I have conducted I lost count, more than 250 sessions now in data science. So I built a model. You know what's coming, right? So looking at the place, the position people occupy in the class, I can guess a lot of things about the person. Believe me, we all follow patterns, and you'll be surprised. I've noticed this pattern without fail. Based on the position people occupy in the class, okay, of course, latecomers, they don't have a choice, but people who come early, okay, based on the positions they occupy, I can draw a lot of conclusions from there, inferences from there, right? So people who are feeling doubtful but are able to ask, they're not asking, I know I can identify such people. Okay. So feel free to ask, okay? All of you, please feel free to ask. Don't get left behind. I was always a backbencher. I was always a member of the backbench society. I'm not saying anything to you. Don't look at me. If you sit in all places means? I was always a backbencher, so I know more over the backbench than the front bench. But other patterns which I observed was during the sessions, right? So a deviation from our main topic of discussion, bottom line is don't hesitate to ask. Okay, feel free to ask, don't restrict. Coming back to this, are you all with me on these two discussions? Okay, now look at this point. You see a red point here, this one. What the model is saying is, as per his income, probability of he belonging to blue class is very high. So the model will pass him as blue. Sorry, in this case green. In this case green. So what the model surface is telling you is predicting the probability of belonging to the green class. It's very high. So the model will classify him as green, but he is actually red. So model has done an error over here. Mistake. Similarly, if you look at this one, this side, the green point here, can you tell me what the model is telling you? The model is telling you the probability of him belonging to green class is very low, so he is likely to be red. But actually he is green. So the model has done an error here, a mistake. Okay? So whenever you have overlapping data sets, as in this case, in spite of the best fit line, the classification, you will find some errors. There will always be errors. These errors are called training errors. Errors in the training data. Okay. All right. No problem. Which one is minus 1? This is 0. This is 0. This is 1. And this axis in this particular picture, this axis is probability of belong to class 1. Okay. That's why your S curve is coming like this. This S curve has been built out of a linear model. If you had taken this, as probability of belonging to class 0, then it would be reverse S curve. Because your curve would be like this, the line would be like that. Oh yeah, all models have problem with outliers.
So can you explain what is the reason you have taken S curve rather than the linear line?
Can somebody answer that question? Why S curve?
Because the linear was going it will go to plus infinity to minus.
Hey, linear will be overfit. Who said that? What did that? In linear models, we don't have any boundary. They go to plus infinity, minus infinity. We don't want that. Probabilities have to be between 0 and 1. That's why they will convert into sigmoid. Sigmoid curve has that property that will always remain between 0 and 1. So we are able to map the numerical values to probability function.
So coming back to the same question, now you explain the binary thing. So same thing is applicable for the multi-class.
Yes, in multi-class classification, it will be 1 versus rest. Suppose I used this logistic regression for OCR, optical character recognition. So you'll have one S curve for A versus others, one S curve for B versus others, so on and so forth. So in your mathematical space, you'll have multiple S curves cutting each other. One is for A versus others, the other one is B versus others, C versus others, so on and so forth. All these algorithms, decision tree, naive Bayes, support vector machines, neural networks, logistic, they all break your mathematical space into compartments. They break them into compartments, pockets, where one pocket belongs to this object, the other pocket belongs to that object. All of them do that. You done decision tree yesterday? Yes. Which data set did you use? Diabetes data, PMA diabetes data set, okay? That is a binary classification actually. And so when you make decision trees, okay, this is the structure you have of decision trees. What you're doing here is, this entire mathematical space is your root node. The entire data set, all data points put together is your root node. Then you find out one particular column on which you break the data into two. That is like putting a vertical boundary here. So these two now are these child nodes. But you have not achieved your what you call homogeneity. Your Gini index is still very high, or entropy is very high. It's still not pure leaf. So what you do is you again find a column here in this data set and break this into two. That means you're drawing a vertical boundary. So this and this is the child node here and here. So decision tree also breaks your mathematical space into pockets such that each pocket becomes homogeneous at leaf level. So right now I have reached the leaf level. Hopefully at leaf level, each pocket is become homogeneous. Now I know what are the conditions under which somebody belongs to this pocket. That is called the rules of the decision tree. All algorithms break your mathematical space into pockets, including logistic regression. You treat A as class 1.
For this family, the default is
this is binary class classification. If you are in multi-class classification, optical character recognition, then you treat at one point in time all data belong to class A, alphabet A as 1, and rest of them are zeros. See what is the boundary. Then treat all the records belonging to class B as 1 and rest of them zeros. Then redraw the boundary. So you'll have multiple boundaries cutting each other.
This is like multiple variables affecting a particular attribute that we're trying to tell. For example, if a customer is fraud or not, if I'm considering age as a factor, I'm also considering gender as a factor. I'm also considering
Yeah, that will be hypersurface. Hypersurface. But multiple hypersurfaces for A, for B, for C. You'll have that, right?
So will that be a consolidated single mathematical space?
Yes, 100%. Yes. The whole model will be a composite of all these surfaces. Okay. Let's move on.
So multi-class is always 1 versus a rest.
Multi-class classification, most of the algorithms give you OVR. OVR means 1 versus rest. Some algorithms give you a facility of replacing the OVR with Bayesian probabilities. Okay, you can actually go and modify that in your hyperparameters. But most of the algorithm by default will give you OVR. Right? Some algorithms like support vector machines, OVR is not very efficient, so they give you another technique called Bayesian probability based. Shall we move on? Okay. It has a gradient descent algorithm working under the hood to find you the best fit line. Right? The linear model uses gradient descent algorithm. Do you remember gradient descent discussion we had yesterday? See, the gradient descent is to find best fit line. I'll quickly summarize this. I know it was too much in one day to cover. Your error function will always have this form, not very difficult, guys. If I give you equation y equal to x square, for any value of x, y will always be positive. It's a squared term. If x is -1, -1 into -1 becomes +1. This is called a convex function. So whenever you have any function raised to power 2, it will always be convex. Right now this is single dimension. This x can be multiple dimensions. So if I take 2 dimensions m and c and plot the error, this will be a bowl shape. Right? Now in this ball shape, we have to reach the global minima. It's guaranteed you will have only one global minima. You won't have any other. For quadratic error expressions, you will always have one global minima guaranteed. Okay. So we start with some random MNC. That random MNC gives us some error. The same concept applies in logistic because logistic is also a linear model. Right? From that MNC, it will come down to this using your partial derivatives. Concept, okay? There's a lot to discuss in this. I'm not going to discuss all those things at this point, but you will need this if you're going to do deep learning, neural networks and all those things. Right? At that time, we'll take it up in detail. Same concept will apply today in logistic because logistic uses linear model under the hood. So it finds for you the best fit line given the spread of the data points in mathematical space or best fit plane or a hyperplane. Once that plane is found, that plane is sent through the sigmoid transformation and it's converted to S curve. Right? Now the driving force behind this, here in this case it was quadratic. In this case, the S curve which is formed, the S curve can be shifted forward, backward, upward, downwards. Let me see if I can show this to you, okay? What happens is, insert, if I take this S curve, I hope it works. Yeah, it works, okay? Now this S curve, you can move it up by changing the C in y equal to mx plus c, or you can move it down. You can flatten it. To flatten it, what do you think we'll use? The slope, m of the line. By changing the slope, I can make it vertical or flatten or move it up and down using c. So by using these two parameters m and c, I will find out which sigmoid surface I get is the best surface. And to find out which is the best sigmoid surface of all the infinite possibilities, it uses a function. That function is called log loss. This is just like your gradient descent, okay? Don't worry about this function, it's actually very easy. Looks dangerous, but actually it's very easy. Now let us look at the log loss function. Looks very dangerous, but it's actually simple, very simple, okay? So Forget the sigma and all these things. Just take the expression yi into log of pi, okay, plus then 1 minus yi into log of 1 minus yi into log of 1 minus pi. Correct? Just look at this expression. What is this y? Y is the target variable. Target variable. We know the target variable ranges from 0 and 1 only. 1 is for green and 0 is for red. So this yi can take a value of 0 or 1. Okay. Now let us look at 4 situations. I'm going to show you 4 cases, and the 4 cases we're going to discuss here. Where is the 4 cases? These are the 4 cases. Look at the first case. In your data, the first test case, these are 4 test records, okay? The first test record has this income. The model is saying the probability belongs to blue class is very high and is actually blue class. No error, 0 error, right? 0 error. Come to this. What is the y value for blue class? 1 into what is the probability? Very high, almost close to 1. Log of a very high number, when log comes close to 1, this is 0. Log of a very high number is 0, close to 0. 2 raised to power 0 is 1. So this is log to the base 2. Okay? So log to the base 2 of a very high number means close to 1, will always be 0. Come to this term. This becomes 1 minus 1. We don't even need to evaluate because this is 0. So when you do correct classification for the blue points, your error is 0. Let's take the next case. The next case is this red point. Let's take this red point. Let's take the case number 3. Or let's take case number 2, the second case. Okay? As per the model, given his income, the probability of him belonging to blue class is very low. Which means the model is predicting that he belongs to the red class. As per the income group of this person, the model is a blue line. It's saying probability of him belonging to blue class is very low. Anything below 0.5 is very low. So the model is predicting that this guy is going to be red, but actually he is blue. So let's see what the equation says. He is blue, value is 1. Probability is very low that he belongs to blue class. The model is saying probability is very low. Log of a very small number is a very large number. So this is into a large number. Okay? Since he is a blue class, this expression we don't even need to evaluate. It will be 0. So whenever you do misclassification of the blue, you get a very large error. All right? So the more the blue class is on this side, larger the error will become. So in technical parlance, what we say is, more confident this algorithm is about a particular classification, which we know is wrong, more the error it does. Right?
So if the probability is less, because in this PI will be, if it goes lesser, then the large number becomes more large.
Yeah, correct.
The error will go more. If you go down, it will still further.
So for this blue point, where the probability of him belonging to blue class is almost 0, this error will be very high.
So what we are saying is more error we do on this side.
For blue class.
For blue class, then loss is more.
Yeah, exactly.
And upper side, even the error is there, but loss is less.
We'll come to that. We'll first discuss only the blue class. The more blue points are on this side, in this case, the more the errors will come out. Larger the error will be. Okay? Now look at this, the red one, the fourth one. Or let's take the third one. We know that this guy is a defaulter. The class is red. The model is given the income, the model is predicting he's going to be defaulter. Come to this equation. What is the label value for this guy? Class red, 0. So this expression becomes 0. We don't even need to evaluate. Come to this guy. 1 minus 0 is 1 into log of a very small number. Number minus 1 becomes almost 1. So this expression turns out to be 0. Log of a very large number, okay, is 0. So this expression comes too close to 0. For red classification, we use this part of the equation. For blue classification, we use this part of the equation. Take the last case where the red class is misclassified. The model is saying he belongs to blue class.
So one question. So PI is a probability, right?
Of belonging to blue class.
Belonging to blue class. That's why it is 0.
Yeah. See, the model, the surface is probability of belonging to blue class.
Okay. That's why it is 0.
Yeah, exactly.
For the right.
Exactly. Look at the last case. Last case is the fourth case, where the fourth case is misclassification of red. So when you do misclassification of red, this expression is not for red, so forget it. Come to this. This is 1 minus 0 into log to the base 2. This is a very high probability which your model is predicting. So this becomes a very small number. Log of a small number is a very large number. So error is very large. That's all this equation is. So you sum up the errors done across all the data points, those which are correctly classified, those which are not correctly classified, sum it up, you will get the total error across the entire model. Sum of squared errors, same way this. So the objective is to minimize the sum of squared errors by finding the right logistic surface given the classes.
And so the gradient distribution is the same. Right? So suppose it's a high loss, and it will go in a direction where it want to reduce that loss.
Reduce the total loss. Correct. Yesterday, the sum of squared errors was driving the gradient descent. Here, this will drive the gradient descent.
So it does gradient descent first to get the linear equation and then does the second to get the sigmoid.
Right, sigmoid curve. Both happen together actually, both happen together. It's not one after the other, both happen together simultaneously.
So what is the range for this block? Specific to the data?
0 and 1. All 100% is your complete loss. Which will happen when you have all the red 7 classified as blue and all the blue 7 classified as red.
Logic sheet always places 0.
Yeah, for classification, always 0. All right, shall we move on? Extension of linear model that we saw yesterday. The beauty of logistic regression is it makes no assumption about the distribution of classes in the feature space. Many of these algorithms, linear model especially, if you're building linear classifiers or linear regression, they expect Gaussian distributions. You understand the term Gaussian distribution, all of you? No? Okay. When you build any model, expectation is if you take this attribute, the data will be spread around the central value of this attribute with some standard deviations. Same way, this attribute will have a distribution with standard deviations. When you plot this together in the mathematical space, they will look like, if they are independent of each other, they will look like this. We already discussed this. This kind of a distribution is called Gaussian. So in 3D, it looks like a bell curve. All right. This algorithm does not make any such assumptions, but keep in mind, if you have outliers in your data set, even this algorithm will fall on its face because it is based on linear model. So those outliers have to be addressed. What will happen if you have outliers? If you have outliers, you're likely to have outliers for, say, for example, what do you call them? The class 1. If you have an extreme outlier here, then you're in trouble. If you have outlier on this side, no problem. If you have outlier on this side, you have a problem. So more extreme it is, more severe the outliers is, more the errors will be. Right? Okay. You can do multi-class classification using either binomial distribution in this case or multinomial distribution also is possible. You can also print out the probability values if you're not interested in the class, but I want the probability values. What is the probability belongs to this class or that class? Quick to learn because it's based on linear model, and you have gradient descent to help us out to find the best fit line quickly. Fast in your test data also. In test data also it's very fast. And as I said, many times I have personally seen logistic regression stands out among the top few in many of the situations. Resistant to overfitting, because as a simple linear model, linear models cannot be very complex shapes. It is resistant to overfitting. Okay. Resistant to overfitting does not mean resistant to bias errors. It means resistant to variance errors, right? But we have another one to deal with. And you can print out the coefficients, the probability values, and interpret the probability values. So the model is not a black box, right? Disadvantage in classifications is it uses linear boundaries. What it means is, if the distribution of the classes is something like this, then the model will suffer. Right now we took a linearly separable this thing, but what if the distribution is not linearly separable? Then logistic regression will suffer. If the distribution was like this with overlap, but it was like this, then it will do well. But if the distribution like this on the attribute you have decided, you see the difference? The difference is, if I plot the density graph, okay, in this case, the two density curves are overlapping. Your t-test, analysis of variance, and all these things will tell you that this record belongs to this class, that class, 50-50. It will not be able to classify. On the other hand, if I look at this situation, your overlap is there, but the central values are shifted apart. So when we have distributions which are linearly separable, may not be 100%, then logistic will do well. But you have distributions like this. I don't know whether you noticed, PIMA dataset is like this. That is why in PIMA dataset, you will not be able to get accuracy beyond 70%, 76%. Do whatever you can, right? So, it will not give you beyond 75. When the data distribution is like this, none of the algorithms will be able to help you out.
When we start building this model, we need to check what our data distribution is like.
100% you have to know your data before you start building the models. You have to know your data, which means you have to know every attribute, how the data is distributed, if you're in classification, how the classes are distributed, which dimensions or which attributes are able to linearly separate the two classes. Use only those for your classification models. You have some attribute where both the classes are significantly overlapping, including the central values. Using such attributes for building model is useless, and PIMA Indians, you will see all the dimensions are like that.
So then what we can do actually? We can't do anything. No other algorithm.
No algorithm. Okay. What human brain cannot do, an algorithm cannot do. So you have to have at least one attribute, as you will notice in another data set that is called bank.csv. There also the data overlaps on all the dimensions between the two classes. But there are few dimensions, 2 or 3, where the data central values are separated apart. Based on this 3, it gives you 96% accuracy.
So for our model, we should consider only those.
Only those, yeah, correct. You don't need to include all of it.
What is the name of that Band plots is that two attributes. What in the data
Some
set?
attributes, I'm just randomly taking.
What is that term plot? Gross error?
This is scatter plot. This is scatter plot. Now you find out how the density of the plot changes when you move from this direction to this direction. You will see that the density is very low, very low, very low, increases very high, highest, then it starts falling. So when you convert this into 3D, it becomes a normal distribution. In 3D, this becomes a normal. That is called density function. 3D.
So can't switch the axis for analysis in this case?
Can be.
Can't we switch the axis for analysis?
Switch means?
Say y-axis becomes x-axis so that you are distributing.
What you're basically saying is, no, I'm comparing these two with this over here. This axis is not there. I'm just saying, if you have a distribution like this, your logistic will do well. If you have a distribution like this, your logistic will suffer. Any algorithm will suffer. Okay? But what you're saying is, can't we switch to this axis where the two classes are separated out? That's what you should be doing. So if you have two axes, two attributes, on one attribute they are not linearly separable at all, but on the other attribute they are linearly separable, use the other one. That's what I'm saying. Yeah, all right.
In 2 dimensions, you can see like this. You can change to 3 dimensions. You can see some of the data are up.
So use that dimension, which is helping you to separate out the two. Don't use this dimension.
Can we apply one model on one attribute and another attribute?
That is what random forest does. Random forest, every node of the forest is constructed using randomly selected features from the data set. Yeah, it internally does that. But random forest is the only one which comes close to what you're asking. No, it doesn't do that. It randomly picks up. It doesn't see whether these are the best attributes. All right. Okay, let's move. Let's do a hands-on. This is the same data set. P-Mandian's diabetes data set. Same data set. Shall we do a hands-on on this? Okay. All right, guys, are you all ready? Okay. So if you have access to the code, the first line is matplotlib. We already know what it means. I'm importing from scikit-learn linear model logistic regression. Yesterday we had imported linear regression. Okay. Then I'm importing matplot, SPLT, Seaborn. I use Seaborn libraries for my plots. Especially pair plot comes out very well in this. So I'm going to use this. Train test plot, you already know what it is. Numerical Python. And to measure the accuracy of the model, I'm going to use metrics. So whenever you're doing classification, one of the most important tools for evaluating a model is your confusion matrix. Okay. So that comes through this metrics library. We'll see all those things down the line. Earlier, this PIMA diabetes used to be available in UCI dataset, but now I think it has been removed or archived. So it's not available, but I downloaded it from kaggle.com, another site. I'm loading the dataset over here. It's a data file, it's a text file. While loading the data file, I'm feeding the column names here, which I got from the original source, the column names. So the column names are, the first column name is pregnancy. How many times? By the way, this particular test was done amongst Pima tribes, a tribe in South America, where apparently the ladies are prone to type 2 diabetes very early in age. So this research was done by this university where the objective was, can we build a model and predict who is going to have type 2 diabetes by the teenage? Okay, for that they did research on that community. Some of them were diabetic, some of them were not diabetic, and the characteristics that were captured are these. The first one is number of times pregnancy reported by the subject. The next one is plasma level in your body. Plasma is a component of the blood. Then we have blood pressure. This is diastolic blood pressure. This one is diastolic blood pressure. Then we have skin, where apparently people suffering from type 2 diabetes in that tribe, they have some kind of skin folds. This is measurement of that. Then they do some testing. This is called fasting sugar test or something. That is this test. Body mass index. PEDI is another test. Some pedigree test they do, I think. It's another test related to blood sugar. Age. And the last one is your target column. Whether this person was diabetic or non-diabetic. Diabetic means 1, non-diabetic is 0. Now the whole thing, that the objective is, we are trying to find out, is there a relationship between the independent variables and the target variable? What is that relationship we are trying to find out? That relationship we assume exists in the universe, in the real world. We are trying to find out whether we can discover that relationship. So for that, we are building this model. And I always do this based on the experience on car MPG dataset. When you look for this head, okay, when you look for some sample records, you see all numerical values. But what is a guarantee that there is no record further down which has some non-numerical values sitting in the numerical columns? What is the guarantee? How do you identify that? To identify that, we can use this method. What I'm doing is, I'm using a numerical Python function isReal. This function is a binary function. It's a Boolean function. It will give true or false. This function, I'm applying it onto, look at this apply. I'm applying it onto all the rows, all the columns of this. This is the beauty of Python, where you have to do minimal coding. If you had to do this in Java, you'll probably write a for next within a for next over here. So all that thing is taken care of. So what's happening is, I'm going to apply this function isReal on all the rows, all the columns of PMADF. Okay, and you see this tilde over here. This is a NOT operation. I want only those records where it returns a false. Okay, fortunately there are no records where it returns a false, which means all records, all columns are numericals. What is the other way of finding out whether any such non-numerical characters have come into the data?
Data types.
DF types, that's it. DF types, when you do, it will return the data types of all the columns. If there is any non-numerical value in any of these columns, it will return it as object. That is easier than this, DF types.
So what we do if there is a non-numerical?
What we do if there is a, we have to go and identify the record, convert that into NA, NaN, numerical. Then you can replace with median, mean, whatever replacement strategy. We don't have any such case right now, okay? But we have nothing to be happy about because we're seeing a lot of zeros. And zeros in blood pressure is surprising. It can't be, not possible. 0 in plasma is not possible. But you have 0 values in blood pressure, you have 0 values in plasma. So missing values are there. The missing values will cause problems. We need to address the missing values. Okay, let's move on. Do a diff describe how the data is distributed on the various dimensions. Univariate analysis. If you don't like this, don't do it. Do the pair plot. Pair plot also gives you visually the same univariate analysis. Okay. So I'll quickly tell you one. Look at the difference between, for the test data, the test attribute, look at the difference between the mean, 80, almost 80, and the median, 30. The mean is drastically shifted away from the median on the higher side, which means there is going to be some long tails on the right side, on the higher side. Mean gets easily impacted by outliers. So some outlier is pulling mean towards the right side. How do you confirm that? Look at the distance between the third quartile and this. Look at this. Correct. Look at, you're like me, you don't want to calculate? Can you tell me how long is long? The right side tail, look at the length and compare that to the left side tail. Left side there is no tail. 719 units. So is this possible or is this a typo? We need to go and check. Maybe this is a typo. We don't know. Okay, right, I'm going to move on. The next thing that you have to do is first understand how the data is distributed on your various dimensions. If you think there are outliers, we need to address outliers. We already know we have missing values, we need to address missing values. The next thing you need to do is, since you're in classification, how many records are available for each class in the data set? Look at that. The number of cases for non-diabetic, 0, is 500, whereas the number of cases for diabetic is half of that, almost half. You are preparing for your board exams, and most of the questions that you solve, practice on, is calculus. A small part you do it on trigonometry. Obviously, you're going to flunk in trigonometry, right? Why? Because the pattern of questions that come to you in the exams in trigonometry may not have been reflected by the patterns that you have used. Which means you have not gone through all the possible patterns in the trigonometry questions. Same thing will happen here. To the model, I have given only 268 of the diabetic cases. Maybe this 268 does not reflect all possible permutations that lead to diabetes. So the model will perform poorly in predicting the diabetic cases. It will perform relatively well in predicting the non-diabetic cases, but I want the reverse. The objective is the reverse. Okay? And keep in mind, whenever you're in classification and the classes are skewed like this, all algorithms are biased towards the higher represented class. All models, the objective is to minimize the overall misclassification. So their focus will be on the higher class. So this is another source of bias which comes into the model where the algorithms themselves are biased. So how do you handle this? Make 502? Yeah. We call this strategy upsampling, downsampling. Okay, there is a strategy called upsampling, downsampling, which I will refer to, which I will take you through when we do FMT, model tuning, but right now we are not going to do that. There is a package available, it's called imlearn, but right now we are going to live with this. There is another way of improving the the classification, performing better in the underrepresented class, that is called modifying thresholds. In logistic regression, naive Bayes, any other probability based model, the cutoff is 50%. If the probability of belonging to blue class is 51%, the data point will be classified as blue. If the probability of belonging to the blue class is 49%, the data point will be classified as red. So the boundary is at 50%. Okay, I can modify the boundary. Though none of the algorithms allow me to modify the boundary directly, I can build wrapper class around the algorithms. I build the model. Around the model, I write my own class where I modify the threshold. Okay. Once again, I'll cover this in FMT, not now. It'll be too much. So we can play around with the threshold, modify the thresholds to improve the accuracy of the underrepresented class. We can do that. Okay. How do we do that? We'll take it later. But whenever you see in classification skewed distributions like this, be ready. There's no way you can achieve a very high accuracy for the underrepresented class unless you play around with these two techniques. Let's move on. So this is my pair plot. Okay, I don't like this. So let me quickly redo this. All right, I'm going to come into, I'm not going to do all this, I'm going to come straight to this where I'm going to say SNS pair plot, comma, dag underscore kind is equal to KDE, kernel density estimate. Since these are numerical values, it makes sense to have this. And hue means color, is equal to the last one, what we call it, target class. So hue is equal to class.
You haven't treated outliers
Not
or
yet.
the zero values.
Not
So you just
Yeah, on the raw data. It'll take some time. It's fast actually. Yeah, there you go. Now let us understand this pair plot. All of you have it? Let's look at the very first dimension. The first dimension here is pregnancy reported. Okay. The blue is non-diabetic class, and the red one is the diabetic class. The orange is the diabetic class. Okay. If you look at it, the two distributions are overlapping with the central values. They're overlapping. Very small separation over here. Come to the next dimension. The next dimension is your plasma. Plasma, you see long tails on the left side with a small bump. This is their outliers, the zero values. But otherwise, both the classes, the blue class is perfectly, it looks like almost like your normal curve. And the central values are overlapping. The central values are eclipsed. So once again, not a very good attribute, but at least we have some differentiator here. Look at this one. Even the outliers are overlapping. This is your blood pressure. These are the zero blood pressure cases. They are also overlapping. Yeah. So there is no way your blood pressure will be able to separate out. Based on blood pressure, you cannot distinguish diabetic versus non-diabetic. There's no way you can.
No, but if you correct those zero values,
Still, whatever technique you apply will be same technique. So both of them will shift together, right? So we have a problem there. Look at the next one. This is even more surprising. Almost gone. Skin color, not skin color. This is skin fold. Yeah, you see the same problem here also. Every dimension you look at it, every dimension has this problem. On none of the dimensions, except for a few dimensions where you see small difference in the two classes, none of the dimensions are separating the two classes out. So even you put all these dimensions together and build a model, we are not going to have anything. Yeah, it's overlap, almost this case, the previous case, this one. And that's what we are seeing here. The two classes are overlapping on every day. They are not shifted like this. Let's go ahead and build a model. Let's not be very hopeful about this. Any model will give a problem here. So what I'm doing here is, this is not required. It's not required to be done. All algorithms can take as input the data frame itself. But earlier I used to do this as a practice, where I'm converting the data frame into an array. So data frame minus the column headers is called an array. Okay. And that array, I'm taking the independent attributes into X and dependent attribute in Y. And then I'm splitting this X and Y into train set, test set. Is this part okay with you people? All of you with me on this? All of you, Sairam? You're also on this? Great. Now look at this. I'm instantiating the logistic regression model. You can call it anything you like. I'm calling it model. I'm doing the fit. This is where the best fit line is found and convert into your sigmoid curve. The fit. Once the model has been found, then I make use of the predict function of that object on test. So these are my predicted labels, diabetic, non-diabetic. The actual labels are Y test. Okay. Some people get confused here, so I'm going to stop it. Don't look beyond this. Just stop here. I'm asking you to just look at this part. Till this point, everything is fine? Okay. Now what I can do down is, I can, for the time being, I'll remove this. Okay. I'll put a, yeah. For the time being, just ignore this. Control X. We'll put it over here. Insert cell below and we'll put it here. All right. I'll uncommit it later. I'll do that. Okay. Now look at this. Have you seen confusion matrix before? Yeah. All of you agree it's exactly what it's called? It confuses people a lot, right? Confusion matrix. So what I do is, as a practice, when I make my confusion matrix, I always keep the actuals on this side. Actual diabetic, non-diabetic. And the predicted, the output of the model on this side. Diabetic, non-diabetic. This is my practice. You can follow the other way. But whichever way you follow, follow only one. How do you control this? Since again Y test first, this is actual, it goes to the rows. Y predict next, this is your predicted values, goes into the columns. If you flip this, you'll flip that. Now what it's saying is, of the 147 diabetic cases in your, sorry, this is non-diabetic, not diabetic, this is ND, non-diabetic, this is diabetic, ND, D. Awfully sorry. If you go and read the source of the data, they are very clearly told 0 is non-diabetic, 1 is diabetic. Of the 147 non-diabetic in your test data, 132 have been classified as non-diabetic. No mistakes. For this class, true positives. Of the 147, 15 have been identified as diabetic. Incorrect classification. These are those values of red lying on the extreme end, values of blue lying on the extreme end. Look at the diabetic class. 84. There are 84 diabetic cases in your test data. Of this 84, 46 have been correctly classified as diabetic. 84 minus 46 is 38. 38 have been misclassified. Okay? Now look at this. Now look at this. What is the overall accuracy? 77%. Looks decent. But let's look at accuracy in diabetic class. Okay? We call it recall. Recall is, the formula for recall is true positives by true positives plus false negatives. Looks very hi-fi, but what it means is true positives divided by row total. So the recall is 46 divided by true positives plus false negatives. This is false negatives. For this class, this is false negative, right? So yeah, so it is 46 plus 38 back to 84. That comes to around 55%. Hey. It's coming like 55, 54%, right? That is like tossing a coin, heads or tails. You don't need a model for this. Right? So to get this kind of accuracy, you don't need a model. You can just toss a coin and say diabetic, non-diabetic. That is what this is. So overall looks great, but don't get fooled by this. What is important is this, but this is what we expected because this is represented very poorly, the diabetic class. This is important for us. Look at the recall for the non-diabetic class. Non-diabetic class, the recall is 132 by 147. This will come very high, 90%, 80%, 90% roughly round. So the recall for the non-diabetic class is very high. Recall for the diabetic class is extremely poor. But that's what you should expect. We wanted the reverse. So that's what will happen when you have situations like this. Okay? There is no way you can get a very good model when the individual attributes are poor attributes and the classes are underrepresented. You can't do it. So The magic happens in the data. How do you prepare your data for analytics? That is where the magic is. It is not in the algorithms. Okay? It depends on data preparation. 80% of our project estimated effort in data science goes into preparing the data. Running the algorithm is matter. Then rest around 15 to 20% goes into fine-tuning a model. It goes into that. All right, let's do, there is a function called score. Instead of doing this, I can directly call score, but don't rely on this when you're doing classification. What this function does is, it regenerates the model and then tests it on this test data. It regenerates the model, then compares the test data and this automatically and gives it the score. Okay, so this has nothing to do with confusion matrix. You can actually run this and say remove the hash, run it. It should give you the score. Model is not defined. Why? What spelling mistake? Oh, I have not executed. I'm just showing you this. Okay. I have not executed these lines. So it gives you overall score, but overall score is not reliable, so don't depend on this.